Hello and welcome again. I'm Kieran Maher and this is our Financial Economics Python tutorials. Just jumping straight in, we're carrying on from the last tutorial where we did some simulations from the normal distribution to show the law of large numbers. We're going to start off and do the same thing again, but we're going to draw from the uniform distribution. And then to make clearer what's going on, we're going to look at how this relates to holding different size portfolios and how it relates in particular to avoiding extreme outcomes. So this is the benefit of diversification from a portfolio. You tend to get the average outcome rather than the extreme outcomes. And that's described here in the questions from the tutorial document. We're going to be using a uniform distribution on 0, 4. Remember, a uniform distribution is basically a rectangle. Everything is equally likely. So we'll start by loading our NumPy and Matplot libraries. Now, one of the great things about programming is you don't have to do it from scratch. You can reuse code, both your own and code that you've legally obtained from other people. Lots of people post snippets of code on the web or even whole programs that they're making available in the public domain. We actually have some code that we used ourselves for the normal distribution case, and so we can just reuse that code, and we just want to change this one little bit here. We don't want to draw from a normal distribution, we want to draw from a uniform distribution. So we will do that, and uniform distribution is not parameterized in terms of its mean and variance. 0 and 1 are the mean and variance of a standard normal. The uniform distribution is parameterized over an interval from its lowest bound to its highest bound. It has finite range of values it can take on. We're going to use 0 and 4. That was given to us in the question. So it's going to have a mean of 2. It's going to be symmetric about that. So otherwise, so here we go. Let's change that code. That's right here. We've changed that to uniform, and we've changed the uniform distribution parameters to be 0 and 1, since those are not the mean and variance. Just running through the code quickly, we're going to have different sizes of portfolios now, different sizes of samples, and we're going to draw random returns from an asset, or random numbers. One random number if there's only one asset in the portfolio, 100 random numbers if there's 100 assets in the portfolio, and those would be the returns, the payoffs in our story. And then anything can happen from one draw, so we're going to average and see what's going on. So the question suggested 500, but we can vary that very simply here because we've just made it a parameter. So the number of replications, let's bang it up to 10,000. This is the great thing about programming. It's easy to change that number, and the computer doesn't take hardly any time at all to do simple calculations like this. So we're going to run the for loop. We're going to draw, first of all, the sample, not 500 this time, but 10,000 of the different sizes. And then we're going to take the mean, and then we're going to draw the figures right here inside the loop, so histograms of those distributions. So let's go ahead and do that, and bang, pretty quick. So when you have a sample of size 1 here, you get basically the original distribution out with just a little bit of sampling noise. So that's roughly rectangular on 0 to 4. And I've forced the limit here on the display to go from -1 up to 5, so we're always going to be comparing like with like. Now with sample size 2, we'd expect from the law of large numbers to start to get some concentration. And so you actually see, this is proved in probability and statistics textbooks, that this will be a triangular distribution. And as you increase the sample size, or the size of your portfolio here, size 5, it looks a little bit more bell-shaped. It's also getting tighter. The base is coming in, and we're seeing more mass around that mean of 2. 10, 100 and 1000, it's just a spike very close around 2. So that was very quick because we had a piece of code that already did something similar. Now we've got to do something new. Now we want to look at the probability of the average return being above 3. So that's the probability that the returns of the portfolio will be above 3. And that's going to vary with the size of the portfolio, because we can see it basically in this distribution. Here, when we had portfolios of size 1, 25% roughly of the distribution is above 3. When we had portfolio of size 2, a sample of size 2, you can see it's a much smaller area above 2. And as the sample size got a bit above 3, sorry. And as you can see, as the sample size gets bigger, it's very small, very, very small, and now it's nothing at all, it would seem. So it would converge to 0. So we'd expect this number to look like 0 once we get to 100, or even much smaller number like that. But for much smaller portfolios, it would start off around 25% and drop down towards 0. So it's good to always have an idea about what your code should be producing, especially for your test case, so that you know what's going on. So again, instead of trying to do all of this in one go, let's break it down and do it in steps. So we are going to take 10,000 replications so we can build up a probability, a good estimate of the probability. We don't just want to say yes or no based on 1 or 10. We draw our samples. These are our portfolio asset returns. And in this portfolio, there's only one asset. And we're going to do that 10,000 times, and then we calculate the mean. So this is pretty much the same as before. We can check we've got the right size, and of course. Now we need to work out how many, or the proportion, that are above 3 out of these 10,000 numbers. So there's lots of possible ways of doing this. One of them is with a simple test. So there's a command in NumPy, greater, or a method in NumPy, that allows you to test whether a particular thing, the elements of a particular thing, in this case the array of means, are bigger than something else. So I had to look up how to do that, so I went and looked at the NumPy reference. So just to show you that, we don't have to memorize all these commands. There are all these different kinds of commands here in NumPy that do all kinds of different things. I was looking for greater, so I type it here in the quick search box, and it shows me different things to do with these kind of comparisons related to them. We just want these first ones up here, NumPy greater, for example, and it gives me the code and some examples, definitions of the arguments, what it returns, and some examples. So it's going to return out an array or a scalar depending on how much information we put in. That's good. So we're going to get an array out. That's what we want. And that array, we can see down here, is going to be a Boolean array. So it's true and falses. And remember, true and falses are basically the same as zeros and ones. So if we count up the true cases, we will be counting up ones, and that will tell us how many times we got the thing that we're interested in. And so you can in fact compare arrays with arrays and do all kinds of different comparisons at the same time. We're just going to have a constant, so it's going to be a bit simpler. We're just going to be comparing back here means. There are 10,000 of these, but we're all going to be comparing them with the number 3. We could make comparisons with a whole range of different numbers, but it's pretty simple here. So this will generate an array, which we've called yes-no, to show that it's Boolean, of whether each particular mean is greater than 3 or not. And then the proportion will just be summing up all of the ones in that array. So that's when you add up zeros, you only get 0, so the sum command just does that very simply, and dividing it by the total number of cases. So that's the replications, and that will give us the proportion, which in the limit, if we had an infinite amount of data, would actually converge to the probability. And then finally, we're going to show that. Now, because we're only doing one replication, one portfolio of size 1 and 10,000 replications, we should get a very good estimate of the mass here, sample size 1, above 3. And we'd expect that to be about a quarter. So let's go ahead and do that. And indeed, it is pretty close to a quarter here, 0.2475. And that is just some randomness from getting different samples. If I ran that again, I'd get a slightly different number. Right, so that seems to work. So now we can run some loops over this. But the loop's a little bit complicated, so let's just take an extra step and show how we're going to convert this to a loop. So we need to have an index. That's what the loop would be generating. I'm just going to generate 0. Doesn't have to be the first thing in a loop. We've shown before how you can loop over anything you like, but we're just going to do a standard range command to generate the elements for the index. We're going to do 10,000 replications as before, and then because we need to store the results, we're going to initialize them. So I'm going to have the proportions. They would be different for different values of index. We've only got the 1 here, but I'm going to make the array slightly larger so I can check that nothing funny was going on. I'm going to make the array contain zeros, 2 of them, and then we also want to keep track of the size of the portfolios. And I'm going to put in 2 zeros, and that's where I'm going to put those information. And then a little bit of might seem like redundant code here. I'm putting in the size array, index is index plus 1. And so really the size array is just going to be the numbers 1 to n plus 1, however many cases I decide to do. So why don't I just use the index itself? Well, the problem is that index under the normal Python range command starts at 0, but you can't take a sample of size 0 in from the uniform distribution. So here, if I'm going to start at 0, I have to have 0 plus 1 as my smallest sample size. You could just start index at 1 and write a piece of code that generated your sizes, but we're just going to use the standard thing and a few little adjustments to make it clear what's going on. And then from there, everything's exactly the same. We draw the samples, we take the means of the samples, we see how many of those means are greater than 3, convert that to a proportion, and then pop out the numbers. And so the numbers here are proportion and size. It's 2 arrays of size 2. So the first one is proportion, and so 25%, that's what we'd expect, and nothing has happened to the second element. We made that a 0, and it hasn't changed. What was the size of the sample, or the size of the portfolio? It was 1. And what was the second one? Well, there was no second one, so that stays at 0. So we're checking the code's doing exactly what we wanted. So we're now ready to convert this to a loop. So index, which was just a particular number, is now going to be what we're going to run the loop over. So we're going to have all different. This is going to be tracking all different sizes of portfolios. So that's going to be the for command here. We're going to have the index, and we're going to range from 0 up to max portfolio size -1. So what's the max portfolio size? Well, we'll just define that. We could just put the number in, but again, it's just good practice to pull those out as parameters beforehand and initialize them. So that's an extra one. Replications is 10,000 as before, and then we initialize the 2 things that we're going to use for storing our results. Proportions, which is going to be of max portfolio size, and size, which is also going to be of max portfolio size, and we'll just allocate those to being 0 to start off with. and then we run our code. We take a sample starting at 0 for the index, so 0 plus 1 here is 1. That's our first sample size of 1, and that will run up all the way up to max portfolio size will be the last one, minus 1 plus 1. So in fact that number will be the last element. We take the means along the rows. We do the test to see if they're greater than 3, store the results in yes, no, work out the proportions by dividing yes, no sums by the number of replications. And because we're going to be getting a different number each time through the loop, we store it in an array. So proportions is an array, and we store it in the indexed number. So that'll start off 0, 1, so on, and we also want to keep track of the matching size. And so in size index, we store the size of the portfolio, which is index plus 1. Now, here a little bit of programming aesthetics. I've called things by names so you know what they are. Proportions are proportions, and sizes are sizes. So it's easy to keep track of which variable is stored where. That makes our life easier for working with the data. There's a choice here about whether to store everything in one larger array and have one dimension, one axis of the larger array, which keeps track of which variable you're doing, which basically looks like a data frame or something like that, where you might be thinking of variables rather than just observations being stored. When you've only got a couple of things, it's, I think, easier to keep track of them in separately named things. So I've got 2, so it's easy to just keep track of them in two different arrays. If I had 500, then it might be easier to just have some larger array, some called results, and different bits of the array would keep track of results for different things. So a choice there. If you have only a couple of things, it's all right to just sort of do it by hand, as it were. When you start to have more than 2 or 3, it often becomes worthwhile just to store them in some bigger thing or use a loop. It's the same principle here. Why we're using a for loop? Well, because we want to do this many times. How many is many? Once you're doing something sort of more than 2 or 3 times, it's probably worth writing a loop, because if you change your mind about how you're doing it, it's a pain to have to adjust 4 separate lots of code or 5 separate lots of code, let alone 1,000 separate lots of code. So let's run this. Taking a minute to run. Did I actually? Maybe I didn't. Oh, I have run it. So, and then here we're going to draw the plot. And as we conjectured, we start off around 25%, 0.25 probability, and it drops down towards 0 pretty rapidly. And so that's what we saw. So this is basically the benefit of diversification. These assets in the portfolio are independent. We didn't have them correlated. And so when you only have a few assets, there's a lot of variability. But as you get more and more assets from that law of large numbers, the average return, which is the return on your portfolio overall, tends to be pretty close to the average of or the means of those individual assets. And so extreme events become unlikely. So here we've been looking at extreme events in the top tail above 3. It's not super extreme. But we could also think about extreme events in the bottom side of the distribution. So less than 1, so very low returns. And we'd imagine that those should become rare as well. And so if we use exactly the same code, and again this is the benefit of reusable code, all we have to do is just change the test. And so that was in the greater command. We were testing to see if things were greater than 3. Now we're testing to see if they are greater than 1. And so this should go from being a 25% of the time event to being an event that happens pretty much all the time. And so this is because low is the greater than 1 is eliminating the low events and pushing us in around the mean as the size of the portfolio goes up. And here is the result saying exactly this. And so what you see here is also a kind of a rule of thumb about designing portfolios. If you were just a private mum and pop type investor, as people say, one asset is taking a lot of risk, but you don't have to have a portfolio of hundreds or thousands of assets. You can see that you'd expect it to get tight around the mean much faster. The trick here, of course, and this is why this is not real financial advice, is this is under the assumption that those assets are independently distributed. In reality, of course, you have to do some more analysis to check that things are not highly correlated. If you buy all in the same industry, then you're going to have a high level of correlation between the assets, or in interrelated industries. So it's actually a bit harder in practice, and so real financial advice would need to be a little bit more sophisticated than just saying 10 or 20 seems to deal pretty well with the diversification. But this is what the simulations allow us to do, and we could get more realistic by allowing correlation structure, or we could get actual data on real assets and start looking at the distributions of the returns and the covariances between those returns for sets of real assets, which we could calculate from time series of historical data, or at least approximate from time series of historical data. And that's the kind of thing that gets done in industry. All right, that's it for this tutorial. I hope you found that useful.